Hi, my name is Thomas Bordeaux, and this is a lab about observing an object moving at a constant velocity along a straight line. In this lab, we will compare position as a function of time in two cases. 1. An observed scenario that has been conducted, and 2. A simulated scenario calculated using Newton's second law. Doing this helps us to get a better understanding of the principles we are learning about, as well as test our knowledge of those principles. Here is our scenario of observed motion in a demonstration that has been physically conducted. We have a background set up to establish measurable dimensions in our recording. So how do we simulate this observed motion? We know from Newton's second law that the final velocity is equal to the initial velocity plus net force divided by mass times the change in time. Since we're assuming velocity is constant, there must be zero net force on the object, meaning that the net force divided by mass times the change in time component of the above equation simplifies out to be zero, and as such, the equation we use to simulate motion simplifies down to final velocity equals initial velocity. Using this simplified equation, we can calculate the final position as being equal to the initial position plus velocity times the change in time. We now only need two measurements, velocity and change in time, and we can find both of these by using tracker. Here we've established a known measured distance, and axes. The direction of these axes could be flipped, but since we're used to seeing positive to the right, like a coordinate plane, we'll keep it in this way. If you were to flip the x-axis, you would just flip the sign of the position and velocity measurements. From our values measured in tracker, we can create this graph displaying position versus time. And by comparing these measurements, we can calculate velocity. Here we're showing both the average velocity across the entire interval of observed time and the instantaneous velocity, calculated by measuring distance and velocity between a sampling point and the sampling point immediately prior. At this point, you're probably noticing that the first recorded instantaneous velocity is below the average velocity. How could that be? Well, the answer comes down to discrepancies in our sampling process and inaccuracies in picking tracking points using our software. To get a better idea of what an object is doing, we can compute a line of best fit for our instantaneous velocity. It's from this line of best fit that we see a much better representation of the motion of our object. We also see that it isn't actually moving at a constant velocity. And this is because in the real world net force isn't actually zero. In the real world, friction and air resistance are pushing against the object, causing it to decelerate, or rather, accelerate in the negative direction. From our different measured velocities, we can now simulate the motion of an object using glow script. And from those simulations, we can compute the motion of a real object and our simulated object. Here we compare the actual motion of the object with the motion simulated using the first instantaneous velocity. And here we compare the motion of the real object with the motion of the object simulated using the average velocity. We can see a very strong correlation in both of these examples, with the predicted and the observed almost identically matching. I'd like to thank you for watching and leave you with my glow script code.